All right, so you ever look at a periodic table and see all those numbers? Two of them, atomic number and mass number, sound almost the same, right? But here's the crazy part. One is like an atom's permanent ID. It never changes. And the other? That's its weight, and it can change. How is that even possible? Well, today, we're going to crack that code.
So, that's the big question for today. How can an atom of carbon, for instance, always be carbon, but sometimes weigh just a little bit more or a little bit less? It just feels wrong, doesn't it? It's like having a fingerprint that's set in stone, but your weight can kind of fluctuate. That's the mystery we're diving into.
Okay, so to get to the bottom of this, we've got to meet the cast of characters. Let's do a super fast refresh on who's actually living inside an atom.
You remember these guys, right? We've got our positive protons, our totally neutral neutrons, and the zippy negative electrons. Now, the most important thing to remember here is that the heavy lifters, the protons and neutrons, they're all packed together right in the center in this tiny, dense little ball called the nucleus. The electrons, they're just kind of buzzing around the outside, doing their thing.
All right, first up, let's tackle the big one, arguably the most important number of all. This is the number that defines an atom's very identity.
So, the atomic number, it's beautifully simple. It's just the number of protons in the nucleus. That's it. Nothing else. Don't worry about neutrons, don't worry about electrons. It is only the protons.
You can think of it like this. An atom's atomic number is its unique, unchangeable fingerprint. It's the one thing that tells you what it is. If you've got an atom with 6 protons, it's carbon, period. If you could somehow magically stick another proton in there, well, it wouldn't be heavy carbon. No, you've created a totally new element. Now it's nitrogen. You've literally changed its identity.
And this rule is 100% consistent across the board. Hydrogen is atomic number 1 because, you guessed it, 1 proton. Carbon is number 6 because it has 6 protons. Oxygen, number 8, 8 protons. See the pattern? The atomic number is the proton count. That is the one unbreakable rule in chemistry.
Okay, so if the atomic number locks in the identity, what's the deal with that other number? Let's get to the second part of our puzzle, the number that tells us about an atom's weight. Or, to be a little more precise, its mass.
The mass number is more of a team effort. It's the total count of all the heavy stuff in the nucleus. So, what you do is you take your number of protons and you add the number of neutrons. That grand total, that's your mass number.
Now, I know what you're thinking. Hey, wait a minute, what about the electrons? And that's a great question. The simple answer is they're just too lightweight to matter for this calculation. A single proton or neutron is almost 2,000 times heavier than an electron. So when we're calculating the mass number, adding in electrons is kind of like trying to weigh a bowling ball and then worrying about a single feather that landed on it. Their contribution is practically zero.
So let's walk through a real example with a standard carbon atom. First, we know it has 6 protons, right? That's its atomic number, its identity. Now, let's say this specific atom also happens to have 6 neutrons. We just add them up. 6 protons plus 6 neutrons gives us a mass number of 12. And that, right there, is why we call it carbon-12.
Okay, so now we have our two main concepts. Atomic number tells us the identity, and mass number tells us the weight. But this is where the plot twist comes in. This is the aha moment that solves our original mystery.
And this brings us right back to our big question. If carbon's identity is locked in stone at 6 protons, how in the world can we have something like carbon-14, which is obviously heavier than the carbon-12 we just talked about? If the proton count can't change, then something else must be different, right?
And here it is. Here's our answer. Isotopes. Isotopes are basically different versions of the same element. Think of them like family members. They all have the exact same number of protons, which is why they're all, say, carbon, but they have a different number of neutrons, and that's what changes their weight.
Let's go back to our carbon family to see this in action. On the one hand, you have carbon-12. It's got 6 protons and 6 neutrons. Simple enough. But then you have its sibling, carbon-14. Now look closely. It also has 6 protons. That's why it's still called carbon. But it's packing 8 neutrons instead of 6. So same identity, different weight. That's what an isotope is.
So, let's boil this all down. For any group of isotopes, the atomic number is exactly the same. That means the element is the same. But because that neutron count can be different, the mass number and, of course, the weight is different. That's the whole secret. So, okay, puzzle solved. But you might be thinking, why does any of this actually matter in the real world? Well, let's pull it all together and see. This table right here is pretty much the ultimate cheat sheet. Let's break it down. The atomic number, it only counts protons. It identifies the element itself, and it can never change for that element. You'll find it right there on the periodic table. Now, the mass number, that counts protons plus neutrons. It identifies a specific isotope of an element, and yes, it can change. You usually see it in the isotope's name, like carbon-12 or the famous uranium-235.
And believe me, this isn't just for textbooks. Scientists use this stuff for everything. It's how they identify elements for sure, but it's also fundamental to nuclear science, because the number of neutrons can determine if an atom is stable or radioactive. In fact, that tiny difference between carbon-12 and carbon-14, that's the entire basis for carbon dating, which lets us look thousands of years into the past. Pretty amazing.
It's really incredible when you stop and think about it, isn't it? Just two little numbers, and they hold a universe of information about an atom's identity, its family, and how it's going to behave. It's the bedrock of all chemistry.
So we've figured out how two simple numbers can define the identity and weight of every single atom. But it kind of makes you wonder, right? If just adding one or two extra little neutrons can change an atom's properties so dramatically, what other tiny hidden variables are out there shaping the entire universe around us? Definitely something to think about.